Alright, so we're starting 8.3 and a lot of the rest of this chapter, I believe, has vectors in it. And other uses of our trigonometry. So in math, in life, we have a lot of quantities that we have. I could have 10 apples. Something could weigh 130 pounds. I could be driving 75 miles an hour. These are all called, when we have a quantity represented by a real number. We call them scalars. Color. Another example of this is the Richter scale. Earthquake. Magnitude system. So like a 7.2 earthquake. It's called a scalar. Another word for it though, and this is the reason why I brought up the Richter scale, is we could also call it magnitude. Magnitude is how large is it? Or high. In terms of the number. Let's go back to that 75 miles an hour. 75 miles per hour gives us some information about what I'm doing. If I'm driving this, gives us some information about what I'm doing. I'm driving somewhere with an average speed. What is missing from that? Direction. Hey, boy, where the fuck am I going? Am I going in a circle? Am I going in a straight line? What's going on? So what's missing is direction. So a vector has both magnitude and direction. If I said 75 miles per hour southbound, now you know which direction I'm going. I'm not going to Sacramento, sounds like I'm going to Los Angeles. Right? Two different areas, I could have been headed to the Bay, I could have been headed to Vegas. Yeah. Picking a direction takes me in an entirely different spot, so. We do vectors for a lot of stuff. Most stuff in real life, when you're doing the mathematics for it, you end up resulting down to vectors. Because a lot of times it's not just the magnitude of something, but the direction is important. So how do we represent vectors? We represent vectors with arrows. Yeah,
Is it always magnitude or is it sometimes like a speed?
well, it's always called magnitude, it could be the speed. Like in terms of me driving somewhere, the magnitude is the speed. But if I'm talking about like the force of gravity, gravity has a direction and a magnitude. But we're not, it's not like it's a different unit. So we represent vectors with arrows where the length is the magnitude. Represents the magnitude. And I hope this is obvious, but the direction of the arrow is the direction. Points in a direction. You guys ready? Yeah. If I give it the starting point a letter and the ending point a letter. We call this starting point. It's called the initial point. And the ending point. Is called the terminal point. The way we name a vector, if we have 2 points and we're using it for the start and the end. Is we say the letter where it starts at, the letter where it ends at. And you can put an arrow above it to indicate a vector. Now, for me, I'm not a big fan of the bottom half of that arrow. Because it tends to get in the way, it makes it look like an apostrophe or sometimes part of the number, it's confusing, so I tend to do this. These are equivalent. if I said BA. It's a vector that starts at B and goes to A. And they should be right on top of each other, but they don't actually need to be. Well, they should be for BA to be that, yeah. I'm saying they start and end at the same point. I could have another vector. Let's see if I can try to get it the same length and direction. If two vectors have the same magnitude and direction. They are equal. They don't have to overlap. Don't have to be in the same spot. So AB, assuming I make them the same angle and direction. AB is equal to CD. Two vectors of equal magnitude. But opposite direction. Are called opposite vectors. So if I moved BA over here to kind of illustrate it. I could say BA equals. The way we do it, we would say negative CD. Now, you might imagine naming vectors after two letters gets tedious after a while. So. There is another naming convention. If we don't have the names of the points. The two endpoints. We can call a vector single letter. Vector B. B is a common one to use. Another common one to use is U and W, just because they're not used very often for other things. Alright, so next topic, adding and subtracting vectors. Well, first off, if I add a vector and its opposite, I get 0. Two opposite vectors add to 0. Now, I don't think 8.3 uses a coordinate system yet. But we do in 8.4 and 8.5, so I'm gonna introduce the idea, but I don't think you have it in the homework for it. Let's say. Student page. Let's say I have vector u. And. It has a direction or. Has a coordinate system like this. It looks like an ordered pair. But arrows instead of parentheses. What the 1, 4 is showing. Is the x and y values if I made a triangle. For the vector. This is vector u. It goes 1 in the x direction. And 4 in y direction. I was about to say, wake up. And it did it for me, didn't it? That's a fucking loud ass chime. So I'm gonna use B as well, because we're gonna do some vector addition and talk about subtraction. Let's say B is 5, 2. A common way of doing this is like having them. A common way of working with this is having them both start at the origin. That was vector u. And that was vector b. Alright, so if I wanna add vector u and v. The vector u plus v. You add the x components, 1 plus 5. And you add the y components, 4 plus 2. And get 6, 6. So if this were x1 and y1. And this were x2 and y2. The vector is x1 plus x2 comma y1 plus y2. And it looks like I need another black line up here for each of those. That is vector u plus v. That's if I have the numbers for the vectors. If I don't have the number of the vectors and I just have 2 arrows for vectors. Looking at the picture, does it kind of like see how we could add them? Any idea how I could go about adding these if I just had the 2 arrows?
Just add it together. Plus B.
But like pictorially, how am I doing that? Like, how do I end up with the green vector starting with the red and the blue vector?
So by adding their x's and y's.
But if you don't have their x's and y's,
If you figure it out by looking at the graph.
you can very much figure it out by looking at the graph. Does anyone see how? Or I explain how? Anyone have an idea? Like without having the green line there, you may not see it. What if I copy u over and made this u, like copy of u? Or I could add a copy of v. So to add them graphically. Go from tip to tail. That's what they tend to say it, where. The tip, this is the tip of, well, let me redraw an arrow. Tip, tail. So you. Take the tail of one, put it at the tip of the other, and you just find the vector from there. So to do MF. So we can do the same thing with subtraction. If I said u minus v. It's doing u minus v. This is the same thing as u plus negative v. Now, before I go to the numbers, because the numbers kind of are going to show us where the arrow ends up. To do this graphically. Do the copy thing like I did, like I was adding it. And then make it point the other direction with the same length. And say this is copy of negative u. Actually, I'm wanting negative v. This is what I just graphed would be v minus u. I'll do that real quick. So this vector here is called v minus u. But I could also do the copy of negative v. And then this vector here going from there to there is gonna be u minus v. So add the negative vector or the opposite vector of one of the other. That's the easiest way to do it graphically, rather than trying to think of it as subtraction. Think of it as adding a vector in the opposite direction. Once you get used to adding vectors by doing tip to tail. Adding one in the opposite direction is fairly easy. Trying to wrap your head around. Subtraction, just looking at it is I can't do it. Maybe you can't. I have to think of it as opposite vectors and then I can do just fine. If I try to think of u minus v without doing u plus negative v. I'll fucking sit here for 10 minutes trying to fucking come up with a way with how that arrow is gonna end up looking. And not get anywhere. You'll notice. That this is the negative of u minus v. They are pointed in the opposite direction, but have the same length. And numerically. U was 1,4, V was 5,2. Doing the subtraction is easy, just do subtraction. 1 minus 5, 4 minus 2. I get negative 4 comma 2. And that looks about right. If I did V minus U. I have 5 minus 1. 2 minus 4. Is 4 negative 2. So write 4 down 2. When you have the numbers, it's easier to see. Easy to spot. One is the negative of the other. By the signs. Still on the first page. Like, there's not a lot of, got a lot of like, here's the topics to do. The rest is a lot of examples for the most part though.
Is there a difference? Like, you might have to, cost. So that separate lines.
This is saying do the operation. This is describing the actual vector.
So
So I'm gonna take the u and v and the u plus v and enlarge them real quick. See when? Oops, it's still right. Yeah,
if the number value that's given for the vector is just one number, that's the distance of the vector.
they will never just give you one number. Cause if they give you just a number, they need to give you a direction. And the direction would have to be given in some way, likely as an angle. Or something like that, as we're about to see. Or doing this ordered pair. So let me redraw U and V. So this is a better way of looking at your question a second ago. U plus V is the name of this vector in the middle. How do I get it? I get it by adding the other two vectors. So what I have here is a parallelogram. Parallelograms are quadrilaterals. With parallel opposite sides. A quadrilateral is a shape with four sides. Hopefully you remember from algebra, parallel. Means they point in the exact same direction. Or opposite. And they don't have to be the same length. I drew them all the same length, but they don't have to be the same length. On a parallelogram, opposite sides are equal. So if I call this U1 and called this U2. V1 and V2. U1 equals U2. V1 equals V2. Opposite angles are equal. So pictorially here, alpha 1 equals alpha 2. beta one equals beta two. As we can see, the diagonal is the sum of the sides. In vector format. And adjacent angles are supplementary. Does anyone remember what that means?
How much one?
They add the 180. Good. So pictorially, alpha one plus beta one equals 180. Alpha one plus beta two equals 180. Any combination of two angles that are next to each other, add the 180. So back to what I had just a little bit ago, U was 1,4. B was 5,2. And U plus V was 6,6. That's kind of what I have written here. This is our diagonal. It's also, when you add two vectors, it's also called the resultant vector. Outcome of adding two vectors. Now, it's common to have it listed as like the outcome, it shows where the two vectors came from. So naming convention. Of the resultant vector. Is often a combination of the two vectors that made it. But it doesn't have to be. I could easily rename the vector W. And have W equal U plus V. And if I add u plus negative u. Jesus. Enough emails today? 1, 4 plus negative 1, 4. I can kind of move the negative inside. And treat this as 1, 4 plus negative 1, negative 4. And if I add those up, I get 0, 0. When you get 0, this is called the 0 vector. And we tend to write it like that. In fact, I think I told you 0 earlier without putting a vector over it. I did. I said AB plus negative AB equals 0. I should add the vector sign to it. That was my bad. It is called a 0 vector. It has no magnitude, so direction is kind of meaningless. But they still call it a vector. And notice what I did here. Before I go into some more topics. I had negative 1, 4, and I said this was negative 1, negative 4. This is like taking negative 1 and multiplying it in. So there's a couple ways that vectors have multiplication involved. Multiplying with vectors. What I have here is called scalar multiplication. It's some scalar amount times the vector. Oop. It maintains direction but changes length. Or magnitude. And if I write B as with the number formation I was talking about earlier, I call it B1 and B2. Then KB is K times V1, K times V2. If K is greater than, it gets bigger or longer. If K is between 0 and 1, it gets shorter. And if K is less than 0, it switches to opposite direction. So if I wanted to say 2 times u. I would have 2 times 1, 4. Is 2, 8. I went from that. To being that. There's other ways to multiply vectors when we have vector times vector. The first one is called the dot product. And we put a dot between them. This is going to result in a scalar. Or just a number without direction. We're going to do that in 8.4. The other one is called the cross product. Okay, so let's say that as u cross c. And this results in a vector. And in terms of math courses, you'll see this in Calc 3 or in a physics course. And with that, I'm gonna hit pause, give you all a break. If you want your test back, come on up.